In this video, we'll review circular trigonometry. We'll start with the definitions and then look at some applications. Now, you may recall that we've done trig before. We did it in math too. But there it was right triangle trig. In right triangle trig, here we have a right triangle, triangle ABC, with C being the right angle and A being the reference angle. Sine is going to be the ratio of opposite to hypotenuse. Cosine is going to be the ratio of adjacent to hypotenuse. And tangent is going to be the ratio of the opposite leg to the adjacent leg. Now, while very helpful, right triangular trig does have some limitations. For instance, you can't have an obtuse angle in a right triangle. Right triangles have one right angle, and by triangle sum theorem, the sum of all three angles have to be 180, which means the sum of the two non-right angles have to add to be 90 also. Well, those angles, if they sum to be 90, they both have to be acute. So you can't have an obtuse angle in a right triangle. Secondly, you can't have a right triangle with a negative angle. Doesn't make sense. And lastly, you can't have a right triangle, or any triangle, with negative lengths. Lengths are always positive measurements. So we have these three limitations. Now, if we redefine it away from right triangular trig, we might be able to remove these restrictions. And that's what we're going to do now. We're going to redefine our trig using circular trig. In circular trig, I have the circle, and the circle down below, we have this point xy, which is on the terminal side of angle theta. And the circle has a radius of r. Now, if I put this information into the picture, let's start with the angle. The angle of rotation, starting from the x-axis, is theta. The point where it ends on that circle is going to be xy. And the radius of the circle, this blue segment, is r. Now, if we look at our old definitions, sine being opposite to hypotenuse, cosine being adjacent to hypotenuse, and tangent being opposite to adjacent, we're going to redefine it. But instead of opposite and adjacent hypotenuse pieces, we're going to redefine it using the coordinate xy and the radius of r. Now, let's put in the picture what xy means. So when we have a point xy, x refers to the horizontal component. So what was the adjacent or the green piece now becomes x. What was the vertical, or what was the opposite, the red piece here, is now the y component. So instead of opposite to hypotenuse for sine, we're going to redefine it using our circular trig parts. What was opposite, the red piece, is now y, and what was the hypotenuse, the blue piece, is now r. So instead of opposite to hypotenuse, sine of theta now becomes y over r. Cosine theta was adjacent to hypotenuse. The adjacent, the green piece, is now x, and the hypotenuse is r. So cosine theta, instead of adjacent to hypotenuse, becomes x over r. Tangent theta was opposite to adjacent, red over green, which in the new definition, tangent theta, now becomes y over x. Now, it may seem weird to redefine it, but there are really some advantages to doing this. The advantages to our new definition is, first off, we can rotate any angle. It can be a positive angle, it can be a negative angle, because on a circle, if you move more than 90 degrees, you're just outside of quadrant 1. If you rotate a negative angle, that just means instead of moving counterclockwise, you move clockwise. You take from the x-axis and move down. In addition, we can now have negative values for x and y. Now, lengths are always positive, but a negative x just means you move to the left instead of to the right. A negative y value means you move down instead of up. So this gives us a whole new set of possibilities. And we're going to take a look at some of those now. So here I have a picture of a circle with the point 0.68 on the terminal side of angle theta. I'm going to go ahead and use this to find the ratios for sine, cosine, and tangent using our new definitions. They're up top. So to begin, I notice that sine and cosine require the radius. I don't have that yet. So I could use Pythagorean theorem, or I could use the radius formula. The radius formula, if I know that the x is 6 and the y is 8, looks like this. R equals the square root of x squared plus y squared. Now the radius formula really is just Pythagorean theorem, but it's already solved for the radius. So if I use the radius formula here, I'm going to say r equals the square root of the quantity, 6 squared, plus 8 squared. Which means r is the square root of 6 squared is 36, 8 squared is 64, which when you add together is 100. And the square root of 100 is 10. Now I'm not going to go plus or minus because you can't have a negative radius. Radiuses are positive measurements. Now I'm ready to go and write my ratios for sine, cosine, and tangent. I know the x, I know the y, and now I know the radius. Sine was y over r, which becomes 8/10. Now 8/10 will reduce, it becomes 4/5. Cosine theta is x over r. X is 6, so this becomes 6/10. and that also reduces, and that becomes 3/5. Tangent theta is y over x, which in this case becomes 8 over 6. 8/6 will again reduce, and this becomes 4/3. Now let's look at an example where the angle, or the coordinate rather, is not in quadrant 1, where we've rotated the angle beyond 90 degrees. Now in this example, we have the point -512. This is in quadrant 2. So with the coordinate -512, let's go ahead and draw on the reference triangle. We see that we are 5 to the left, and we're up 12. Again, I don't know the radius, so I'm going to begin with that. R equals the square root of the quantity x squared plus y squared. So R equals the square root of the quantity -5 squared plus the quantity 12 squared. Now -5 squared is going to be the same as 5 squared. It's 25. So R equals the square root of 25 plus 144, which is the square root of 169, which is going to be 13. Now that I know the radius and I know x and y, I'm ready to write my trig ratios. Sine is y over r, which is going to be 12/13. Cosine theta is going to be x over r. Remember, x is negative here. It's -5. So cosine theta is going to be -5/13. And tangent is going to be -12/5. Again, that 5 is negative. All right, so here's a couple things to keep in mind. When you're solving for an angle of rotation, theta, your calculator is not programmed to look in all 4 quadrants. It doesn't know which quadrant you're looking in. So it's been programmed to look for one quadrant for when sine's positive and one quadrant when cosine or sine's negative. And the same for cosine and tangent. It looks for one place where it's positive and one place where it's negative. It doesn't look at the other 2 possibilities. So for sine, it looks in quadrant 1 when sine's positive. And it looks for an angle in quadrant 4 when sine's negative. Sine being the y pieces, so it needs one where y is positive and one where y is negative. Now this wouldn't work for cosine because for cosine, that's the x values, x would be positive in both quadrants 1 and 4. So for cosine, it looks for a positive angle in quadrant 1 when you have a positive cosine piece, and it looks for quadrant 2 when cosine's negative. For tangent, it goes back to the kind of the definition like it uses for sine. It'll say that if you have a positive tangent, we're going to look in quadrant 1, and a negative tangent is going to look in quadrant 4. Now this is really based on where inverse trig functions are defined. And you'll learn this in math analysis or pre-calculus, that inverse sine is defined in quadrants 1 and 4. Inverse cosine is defined between 0 and pi, which will be quadrants 1 and 2. And inverse tangent is going to be defined between -pi/2 and pi/2, which is quadrants 4 and 1. So how does this help? So to avoid confusion, when we solve for an angle outside of quadrant 1, instead of using theta, we're going to use what we call the reference angle. That's theta prime. That's theta with the little apostrophe if you notice in the symbols. And then you will use theta prime, the reference angle, to find theta. Now this reference angle, theta prime, is defined as a positive acute angle. And it's the angle that takes us to the nearest x-axis. Now there's some important elements here. It has to be a positive acute angle. In addition, it's always to the nearest x-axis, never the y-axis. So here's an angle. We're in quadrant 2. Theta prime is going to be the piece that takes me to the nearest x-axis. That would be this little piece right here. So that's the reference angle. Our angle is less than 180 or less than pi, so it's the piece that takes us to that 180 or the pi. For an angle that's in quadrant 3, we're beyond 180, so it's the piece that's the more than 180 that takes us to back to right nearest x-axis and to our angle. This would be the reference angle here, theta prime. If we're in quadrant 4, we're not quite to 360 yet, so it's the piece that takes us to the 360 right here. So how does knowing the reference angle help you to find the angle? Well, here's what we can do. In degrees, if you're in quadrant 1, the reference angle is theta. Theta is theta prime because you already have an acute angle. So anything in quadrant 1, when you solve for it, it is theta. Now when you get to quadrant 2, you're short of 180. And the piece that how much short you are is going to be that reference angle. So here, theta is going to be 180 minus the theta prime. It's 180 minus your reference angle. Reference angle is how short you are from 180. Whereas in quadrant 3, you're beyond 180. And how much beyond 180 are is your reference angle. So here in quadrant 3, theta is 180 plus theta prime. In quadrant 4, it's 360 minus theta prime because you're short of 360. Now if we do this instead in radians, the only thing we're going to do is you're going to change the 180s into 360s. In radians, 180 degrees is pi, and 360 degrees, a full circle, is 2 pi. So theta is theta prime in quadrant 1. Instead of in quadrant 2, 180 minus theta prime, it's pi minus theta prime. Or pi plus theta prime. Or instead of 360, it's 2 pi minus theta prime. Now let's look at an example where we're actually going to solve for the angles. Here, I've got an angle, it's in quadrant 4, and the coordinate is 3, negative 4. X is 3, y is negative 4. I want to find all three trig ratios, but then I also want to find theta and theta prime. And it says we're going to do it in radians. So, like I did before, I need to find my radius. My x value is 3, my y value is negative 4. So r equals the square root of the quantity, 3 squared plus quantity, negative 4 squared. 3 squared being 9, negative 4 squared is 16. 9 plus 16 is 25, and the square root of 25 is just 5. Remember, it's a positive value because it's a length. Now that I know that, I can write my trig ratios. Sine of theta is going to be y over r, which is going to be negative 4/5. Cosine theta is going to be 3/5, and tangent is going to be negative 4/3. Now I need to pick any one of these three to solve for theta prime. I can use sine, cosine, or tangent. The only thing that I need to be aware of, because we're not in quadrant 1, that when I go to pick one of these and I go to solve it, the way to undo trig when you go to solve for an angle is going to be use inverse trig. And when I do that, as soon as I go to the inverse trig, I'm going to go to theta prime and I'm going to drop my negatives. So let's pick one of these that has a negative. Now again, I could use any of the three. I could use cosine, which is already positive, but I want to pick one that has a negative just to show you. So let's say I'm solving for theta prime, and I use sine of theta. Sine of theta is negative 4/5. Well, if sine of theta is negative 4/5, inverse sine is how I'm going to solve this. And I'm going to call that theta prime. Theta prime is the inverse sine of positive 4/5. Now again, to ensure that I'm finding a positive acute reference angle, I drop the negative. This will force it to be an acute angle. And I'm going to put my calculator in radians. I want to make sure I'm solving in radians. Directions say radians, so I go mode on my calculator and push radians. If I change my mode, and I go inverse sine, on the calculator is usually at second sine, and then 4/5, I'll find that theta prime is about 0.93 radians. Now from the previous slide that we just saw, we can find theta in quadrant 4 knowing what the reference angle is. Here in quadrant 4 we're short of being 2 pi, and the amount we're short is at 0.93, that reference angle. So to find theta in quadrant 4, we go theta is 2 pi minus our theta prime, our reference angle. Which means theta is 2 pi minus 0.93. And if we type that on the calculator, we go 2 times pi minus, and I usually just bring back the previous answer instead of type 0.93. We'll find that the actual reference angle, or the actual angle of revolution, is 5.36 radians. Alright, thank you for watching this video, and hopefully it helped you understand how to do some of your circular trig.